Hello everyone, welcome back to my channel Ordinary Data Scientist, where we talk about data science. So friends, I hope you had revised the concepts discussed in the previous videos like the percentile, quartiles, interquartiles and range, mean, median, modes. I hope you have a good understanding of those concepts, right? So let's quickly cover a few other concepts also that are required to understand the data variance and all. Okay, so what is variance as such? Now let's say if in your class one student, let's say student A got 30% marks, okay, and the topper got 95% marks. So we'll see that the gap is huge. The weakest student and the most intelligent students has a huge variance in their score. This is not very ideal case scenario. Now if you had another case like where the, let's say, topper scored 95 but the lowest score in the class was just 75%. Here the variance is just 25 percentage point. You will say this is a very balanced class. So the variability will help us to understand not just the difference between a topper and the let's say weaker student, but also how data is spread across the middle point. Let's say this middle point is the average of your class. Topper is somewhere here and the weaker is somewhere here. Some students are here, some students here, something like that. So what is the deviation of the students from the middle point or the average will also come under the concept of variability, because it's very important to understand the data spread. Okay, so these are the concepts that we will understand in this video. Okay, cool. Now the first thing that we want to understand is your deviation from the mean. Okay, so these are the 5 data points that you have: 5, 9, 16, 17, 18, and you want to calculate the deviation from the mean. Okay, so the first thing that you will do is calculate the mean, which is your 13. So 13 will be somewhere here. Let's say 13. Now somewhere, let me plot it. Let's say 13 is somewhere here, and then you have all the data points like A, B, C, D, E, F, let's say, and this is your average. Now the C is deviated whatever, C minus 30. Similarly B has deviated B minus 30, A has deviated A minus 30, something like that. Similarly D deviated D minus 13, E deviated E minus 13, and so on and so forth. We can calculate the deviation from the mean, right? We can calculate that. So here we are doing the same only, that 5 deviated 5 minus 13, which is minus 8. That means it's below the mean by 8 units. 5 was somewhere here and 13 was here, so it has a 8 unit gap. Similarly the 18 has 5 units gap, but it went beyond the mean. The closest point to the mean is something, this point, the 16, which is very close to the central point or the average compared to other data points. So this is what we are calculating using the deviation, which is helping us to understand the nature of other data points. Okay, the first thing that we will remember is the mean absolute deviation. Okay, mean absolute deviation. This is the first thing that we'll remember. This is nothing but MAD. Okay, so as I said, here it will be A minus 13, B minus 13, 13 minus D, somewhere like that. So it's nothing but your A minus 13 mod. You will take the mod. It can be positive, negative, but it should always be the mod. Next will be mod B minus 13 up to your mod, let's say f minus 13. All those sum, and then you will divide by n. How many numbers are there? So this is nothing but your mu minus x only, or x minus mu, whatever you write. Okay, so I can write that mad, I can write that mad is equal to sigma of xi minus mu, and then you take the mod divided by n. Yeah, I can write the formula like that, that xi minus mu is nothing but your average, and then you take the mod of that. You do this step for all i's, I is equal to 1 to n, and then you divide by n. This is your mean, absolute because we are taking absolute, and deviation because you are subtracting it from actual number. So this is the first concept, mean, absolute, deviation, mad. Okay, once we understand the mad, there are two other important topics that we need to remember is variance and standard deviation. Okay, now variance, if remember, if it is population variance, we represent it by sigma square, and if it is sample variance, we represent it by small s square. Okay, as this chapter is most related to population analysis, the descriptive statistics, so we'll talk about the population only, sigma, but the formula remains same. Okay, so the variance, so your sigma square is your xi minus mu, and then you will do the square of that divided by n, and you repeat this for all I. So xi minus mu square, and then you sum everything, then divide by n. Okay, okay, this is called variance, and it's denoted by sigma square for population and s square for your sample. So people, if you had noticed, the unit of mean, median, mode, even range, everything will be in the same scale. Let's say if I am talking about salary, my unit will be Indian rupees or even your dollars only. If I say what is the range of the Google salary, you will say 54 lakhs rupees. What is the median of the salary? You might say 25 lakh rupees. Mean, let's say mean was 12 lakh rupees, right? So all was like rupees. But if you consider here, variance will be your rupees square or your dollar square, because this xi is rupees minus your average will be some rupees, and then you will square take the square, so it will be like a square. So that's why variance is not very much useful in real life actually, because it has different unit to measure. That's why we'll take the standard deviation, which will have the same unit and represented by sigma, which is nothing but the same formula, but now we will take the under root. Now it will give me the same unit, Indian rupees, dollar or whatever, but it will give me the same scale, same unit. So this is what is mostly used in our statistics also, that sigma, what is standard deviation. Okay, so please remember this, that the sigma is root under of the sigma square or variance only. Okay, now standard deviation and the variance, where do we generally use it? So there are two theorems which help us to apply the standard deviation method. One is called empirical rule and one is called Chebyshev's theorem. We'll go through this theorem, but before that let's understand one thing. Let's say you have the data spread across the axis like this. Okay, something like this. Your data points are here, there and all, and your mean is somewhere here. Okay, now you want to calculate that, hey, how many data points are there from let's say mu plus x, this is let's say x, and how many data points are there from mu plus y or something like that. You just want to see that, okay, if this is my acceptance range, that from the average, as I said, the average is 4 kg, you can go up to 3.9 to 4.1. So you want to see that how many cricket bats the producer are giving to you, in this range, how many data points are there. Okay, so this is the range that we will calculate using the empirical and Chebyshev theorem. So let's first talk about the empirical rule. So to understand the empirical rule, let's quickly understand the normal distribution first. So this is the curve, and then this is normal distribution. Normal distribution curve. Okay. Normal distribution curve is that this is your number line. Actually, this is your number line, and this y-axis will give you the frequency. Okay, that means that this data point has the highest frequency. This is probably the mode of that, whatever it is, x, it can be x, x1, whatever, but let's say this is the data point which has the highest frequency. Okay, so normal distribution, the characteristic of normal distribution is it's symmetrical across this vertical line. It means this will be the mirror image of left hand side. So this is your normal distribution. We'll study more about this curve in subsequent lecture, but as of now, let's understand this is a normal distribution curve. Okay. Now the empirical rule says that if the central point is your mu, okay, which is nothing but your average, if central point is your mu, and let's say this is your another data point, this is your another data point, and this is your another data point. Similarly, at the same distance, this is another data point, another data point, another data point, and these are data point can be represented as sigma, 2 sigma, and 3 sigma. Similarly, here sigma, 2 sigma, and 3 sigma. The empirical rule says that the area from this sigma to this sigma, if I have this area, okay, this area, the white dotted area, from mu plus minus sigma, your 68% data points will lie there in this region. 68% data points will lie here only in this region. Yeah. Similarly, minus 2 sigma, if I say, 95% data points will fall under that bucket. Means you're from here to here, the red line, from here to here, and then mu plus minus 3 sigma, 99.7% data points will fall under this only, 3 sigma to 3 sigma. This is what empirical rule says. Okay, if the data is normally distributed, it's very, very important that the data should be normally distributed. Now, what is normal distribution? We will read more in detail, but as of now, let's say normal distribution is a bell-shaped curve. It's a bell-shaped curve which is symmetric across this vertical line, which will be symmetric across the vertical line. Okay, bell-shaped curve. Now that this is the empirical theorem, that if the data is normally distributed, then for this range mu plus minus sigma, 68 data points will fall under this range. 95% will fall under this range. 95% will fall under 2 sigma to 2 sigma. and 99.7 will fall under 3 sigma to 3 sigma. Remaining 0.3 will fall somewhere here. Okay, that's the empirical theorem. Now let's quickly see one example. Okay, so I think, yeah, this is the example. A company produces a lightweight valve that is specified to weight this much gram. This should be the weight of that particular valve. Okay, so if I translate this into a business problem, you will say that mu is equal to 1365 gram. Okay, 1365 gram. Unfortunately, because of imperfection in the manufacturing process, not all valves produce weights exactly this much. Yeah, that will be definitely some error. Okay, in fact, weights of the valve produced are normally distributed. So this is important, that this is normally distributed. Okay, with a mean weight of this much gram. So this is your mean weight, that whatever whatever getting produced, the products, their mean is at least 1365 gram, and the standard deviation is 294 gram. So I'll come here, I'll say that the standard deviation is equal to 294 gram. Yeah, 294 gram. Within what range of weight should approximately 95% of the valve weights fall? So I want that 95% data point should fall under what weight? Okay. Now if this is normal distributed, I can draw this curve, and the data point here will be 1365. This is mu. Now 95% data should be in what range? Now as we know that 95%, as per the theory, the 90% range will be mu plus minus 2 sigma. That means this range. So which is nothing but your mu plus minus 2 sigma. Okay. So the right point, the right hand side point will be 365 plus 2 into 294, and your left point will be 365 minus 294. Okay, you can do the calculation and get the numbers here. So this is the range. I will check the solution here. So for example, this is the range, 365 plus minus 294. That means this is the range that you will get the 95% of the weight. Okay, so this is the range. Now let's quickly go through other problem also, like approximately 16% of the weight should be more than what value? Now let's consider the normal distribution. As I said, normal distribution is your symmetry across this vertical line. Okay, now if I say that, hey, this range covers your 68% values, if I say this is your 68%, so mu plus minus sigma gives you 68% of the range. So can I say that 34% here and 34% here? Because symmetry. Now if you apply this logic, people, just zoom in here a little bit, you will literally start seeing the numbers here, right? So example, this is your 34% and this is your 13%, and the remaining will have something. So remaining is nothing but, if I calculate the remaining here, it's nothing but 50% minus 34%, which is nothing but your 16%. The remaining, this sigma and above, this range, just write it here. And this is what we need, that at least 16% should be more than that. Had it been said that 16% should be less than that, we would have considered this range. because it's saying more than that, that means we have to find this data point so that it's more than that. Yeah. So let me quickly repeat what I just said. This divide 50-50% both. The sigma has like 68% range, 34%. And if I minus the 50% from 34, I'll get this remaining 16% here, okay, in this range. So the data point will be your mu plus sigma, and that data point above that there will be at least 16% weights or data points. Yeah, cool. Another problem statement, approximately 0.05% of weight should be less than what value. Now very important to understand the language, that the 0.1.5% should be less than what. Okay, so I'll come back here. Let's take the same example. At least 0.15% should be less than what. Now when I say less, I need to care about the left hand side of the graph. Now we know that from here to here, somewhere sigma, there will be at least 99.7% from here to here. That means the remaining one from here to here, there will be at least 0.3%. That means as it is symmetric, 0.1.5% will be here and 0.15% will be here. As it said lesser than what point, so we need to find this. If it had said bigger than what, then we would have find this point, but now we need to find a point, you know, where we have at least 0.15% lesser data point. So we'll find mu minus 3 sigma. This is the data point. Yeah. So people, all this calculation you just need to think, very basic mathematics you need to apply. Just that you need to plus minus some reason and then probably need to find. Always remember that if it says greater than something, you will talk about right hand side. If it says lesser than something, you will talk about left hand side. Okay, that's the only thing. So we'll talk more examples in future sessions, but let's quickly cover the another theorem, Chebyshev theorem. So people, as I said, this theorem, empirical theorem, is very important, that the data is normally distributed. You know, it should be very symmetric towards the middle point. It should be very symmetric towards the middle point, which is mu. You know, it should be very symmetric. But this is a very ideal case scenario, and this generally doesn't happen every time. So for that, we have a new theorem called Chebyshev. In this theorem, the data can have any shape, literally any shape. It can have multiple maxima, multiple minima and all. It can have any shape. Okay. So the theorem says that no matter what is the shape, no matter, and it can be applied to normal distribution also. But for normal distribution, we already have a very standard method or theorem. That's why we follow the empirical theorem, but the same Chebyshev theorem can also be applied there. This theorem says that at least 1 minus 1 divided by k square values will fall within plus minus k standard deviation. You know, at least 1 minus 1 by k squared values will fall within plus minus k distribution. Okay. So earlier we were seeing that, you know, like empirical, we wrote that mu plus minus sigma 68%. We knew that value, right? To sigma, I said 95%. Mu plus minus 3 sigma, I said 99.7%. This is the empirical theorem. But the Chebyshev theorem says that if you take any plus minus k sigma, then you will have at least 1 minus 1 by k squared data points. You will have at least this many data points. This is what the Chebyshev theorem says. Okay. Now we'll see one practical example. In a computing industry, the average age of professional employees tends to be younger than many other business professionals. Yeah, that's true. Suppose the average age of professional employed by a particular computer firm is 28. So the average is your 28. So let's write it down. Your average age is equal to 28 years. Okay. With a standard deviation of 6 years. Very good. So we'll say that the standard deviation is equal to 6 years. A histogram of professional employees' ages with this firm reveals that the data are not normally distributed. So this is important, that the data is not normally distributed. So that means we cannot apply the empirical theorem. But they find that the range is for 20s and few workers are more than 40. Now it automatically says that apply this theorem to determine within what range of ages would at least 80% of the workers will fall. 80% of the workers will fall. Okay, so we need to find the range between that 80% worker, within the range that 80% worker should fall. That means we need to find, if let's say this is your curve, again it's normal, not normally distributed, you need to find the data point, let's say x1 and x2, between that 80% your data point should fall. Okay, cool. Now can I make some assumption that somewhere here mu will be there. I just making an example or assumption, and let's say k is here and similarly k is here. So can I say that mu, and there is a k value which will give me this range, and where I'll 80% values. Okay, so I want to say that hey, the mu plus minus the k sigma should be equal to, I write the formula first, 1 by 1 minus k square, and this is giving me the 0.8 or 80%. So now let me solve this part first, that 1 minus 1 by k square should be 0.8, and then 1 by k square should be equal to 0.2. That means the k square should be equal to 5. That means k is equal to 2.24. I want to try out k, in such that this range mu plus minus k is giving me 80% of the data. This is the 80% of the data. So I applied that logic and found the value of k. Now to find the range, it will be plus minus k sigma. That means the right hand side point will be plus k sigma, and the left hand side point will be k sigma. Just put the values 28 and 6. 28 plus 2.24 into 6, and here it will be 28 minus 2.24 into 6. You will get the range. Inside this range x1, this is nothing but your x2 and x1. So inside this range your 80% data points will fall. Yeah, so that's how you can apply the Chebyshev theorem. Very interesting to understand, and I see the most of the use case of this theorem will be in the production, industrial engineering, or some other kind of branches. But we also try to observe the data, using normal distribution curve and all. Okay, so very important concept, people, empirical and Chebyshev theorem. I'll request that please practice few other examples also, and try to understand the normal curve and the area under normal curve, like at what point it will be, how much percentage or not. Let's take a pause here. In the next video we'll cover the remaining topics, the similar kind of analysis on group data, and then we'll see some of the shape of the curve, skewness and all. But please revise the concept discussed in this video and the previous video, and I'll see you in the next video.